Hey guys, Mr. Backerberg here. In this video, we're going to look at the intermediate value theorem. So the intermediate value theorem says that a function y equals f of x that is continuous on a closed interval from a to b takes on every single value between f of a and f of b. So we're going to try to take a look at what that means, and we're going to look at it visually. So let's say we had some graph, and it doesn't really matter what our graph looks like, but we want to look at it between the x values of a and the x values of b. So this point right here on the graph at the x value of a would be the point a comma f of a. So a would be the x value and f of a is the y value that we get when we plug in that specific x value. And then if we wanted to look at this x value of b, so our graph is up here, that's the point b comma f of b. So what the intermediate value theorem is saying is if your graph is continuous between these x values of a and b, then at some point your graph is going to have to hit every single y value between f of a and f of b. So in this first example, we're going to look to find out, is there any real number that is exactly 1 less than its cube? So what we're going to do in here is we're going to let our unknown real number represent x. So what we're wondering is there any x value that is exactly 1 less than x cubed, itself cubed? So we're going to take x and we're going to see if it can equal x cubed minus 1, because that's 1 less than its cube. Now really what we could do here is we could get this equation equal to 0 by subtracting that x over to the other side. So this would say 0 equals x cubed minus x minus 1. And then if we think about this as a function, so let's say f of x was this x cubed minus x minus 1. We'd be looking for a 0 of this function, or visually that would be an x-intercept for the graph. So if we graph this out on our calculator, so I've got that function typed in, x cubed minus x minus 1. I'm going to do zoom 6. So taking a look at this picture, I can see on the left-hand side here that these function values are negative, but then as we work our way to the right-hand side, now we've got some positive function values. So because this is a polynomial function, it's going to be continuous for every single x value, meaning that there has to be some x value in here where our graph, where our function hits exactly 0. Now, if I wanted to find that exact value where my function is equal to 0, I do have an option for that on my calculator. I can hit second trace, and then option number 2 helps us find zeros of a function. So what I like to do, it asks for a left bound point, which means a point on the left-hand side of that 0 or of that x-intercept. So I like to move my cursor close to where I think the x-intercept is happening. I hit left a couple of times, hit enter. Then it asks you for a right bound point, so I go back to where I think that x-intercept is happening, but then I hit right a couple of times. I hit enter. We can take a guess, but we don't necessarily need to. We can just hit enter one more time, and the calculator will do the work for us. So that 0, that x value, is about 1.325 if we do a little rounding. So the intermediate value theorem for continuous functions, that's the reason why the graph of a function continuous on a specific interval can't have any breaks in it. That graph has to be connected in a single, smooth, unbroken curve, and it's not going to have any jumps or separate pieces to it. That's going to be it for this video. Thanks for watching.